A very critical thing that what we're going to be doing with fluid dynamics is going to be this idea of control volume. So we need to look at how we can put together control volumes and how they can be used and where situation would be used for all of those. So this is a picture from your textbook, and we have 3 different control volumes. So control volume A is what we would call a fixed, slide skipped up, we call it a fixed control volume. So a fixed control volume is a stationary region of interest. So what we do is we take a look at this, and in fact the way this one's drawn, what we'd be looking at is things that pierce the boundary. So in this specific one here, we would have, as you can see, we have some force from the flow coming in, something from the flow coming out. Right there we pierce some bolts, and so free body diagram, well, we know there's going to be some force in the bolts there. And the reason that we use a fixed control volume is nothing on that's changing. Nothing's moving, there's no reason for it. So if we move to the second one, if we look at B, we call that a moving control volume. So a moving control volume we typically end up using with, obviously, things that move, a ship, a plane, a car. And we match the speed of the control volume to the vehicle. Now, by doing that, what we've basically done is, since our control volume is moving at the same rate as the object that we're looking at, it allows us to snapshot in place what's going on. And so it doesn't move anymore because everything's moving at the same rate. And why do we do that? Well, because in this picture B, we care about the ship, not the ocean. So that way, since we're moving control volume along with the ship, we can study what's happening around the ship and not really worry about what's going on in the ocean, where that ship had only been in the frame for, a brief moment of time as it rolls in one side and not the other. C is what we call a deformable control volume. Deformable. There we go. So a deformable control volume, it's a more advanced concept because it's a control volume, but it's still changing. So what we have here is a piston. And so typically what you'd be looking at is you'd be looking at this area here, and you'd want to know, how's the pressure changing, how's the temperature changing, what's going on with combustion, things like that. Because that is a more advanced concept, we're not really going to be worrying about deformable control volumes in this class. Now what we are going to do is, let's take a look at this guy right here. So I have a nozzle that's shooting a stream of fluid into a vein that's being deflected away from the axis that it's coming in. And so what we need to do now is we need to draw a control volume around this. Now drawing a control volume, as we move on in these problems, it's going to be very important to pick control volumes in such a way that makes solving the problems easier. And as you're going to see in different things, that if we draw a control volume in certain ways, that parts of the problem will drop out. So the important thing to remember with control volume analysis is once you draw the control volume, you really don't care what's going on inside the control volume for the most part. You only care about what's crossing that boundary. So you want to draw it in such a way that you've got less stuff to worry about crossing that boundary. And also, as you're going to see as we put together these equations, it's going to be really important that the fluid is entering and exiting orthogonally or normally to the control volume, because this is going to make the math a little bit easier. So in this case, typically you're looking at the vein, you're probably wanting to figure out, well, how much force is that vein pushing back on the water flow coming through. So we draw a control volume, we'd sit here and go, okay, well, I'm going to draw it here, and typically we use a dotted line. I want to draw it so it's orthogonal to this jet coming in, and then it's orthogonal to that one coming out. So I put it a little bit at an angle. It doesn't matter what these look like for the most part as long as you draw it out. Now typically when I do it, I will put a CV there to remind me it's my control volume. Some problems we'll do later on in piping systems, you might have multiple control volumes, and you just sit there and go, well, that's control volume 1. And so then after that, what that's going to allow you to do is to actually start your free body diagram. Because then when you look at the free body diagram, you've got some velocity coming in, you have some velocity coming out, and you're going to have some reaction force in the x direction, some reaction force in the y direction. Then we can drop down onto, okay, well, sum of all the forces have to be zero, getting right back into that mechanics thing with just that water jet as being the little bit of fluid mechanics into it. So we'll be doing a lot of control volumes going forward.